Okay, Bismillahirrahmanirrahim. So, uh, yesterday I did some work in WaterGEM. I want to remind that work. So, this is the sheet where we have calculated the demand for the whole system by including the leakage in the system. And then I converted these values into different units in order to identify pumps easily in a PDF like this file. So what I did, I just copy this value in the and paste it in the pump definition. I will show you there. And based on that value, I selected this pump. I did some homework in order to uh, save some time and show you some new things in WaterGEM related to pumps. So therefore, I have to show many things today. Mostly continuous water supply system, the intermittent water supply system, and I will also try to include a tank along with the pump, that how the pump should be installed with the tank in order to fulfill the demand of water supply network. So based on this total demand, I have to select a pump, and basically these values are equivalent and equal to each other, just converted into different units. And this is basically by I just multiply with 1.5 in order to get the peak demand for hours. Okay. What I did in the previous class, I took some diner patterns. I assumed that according to our regions, that demands are mostly high in ranging from the 5 to 8, and similarly from 10 to 15, and then 18 to some 22 hours. So based on that, I just assume some values, and then I calculated the elevation of reservoir. I model a pump, a reservoir, and then connected the reservoir with the joint used through pump. And I took this pipe as an imaginary pipe, taking it as a 1000 of diameter, having a 1 meter length, because mostly I'm using here I'm using a submersible pump. So in a submersible pump, mostly the pump is submerged in a water. So therefore, no need to connect a pump with a reservoir. Therefore, I'm just assuming or modeling, considering an imaginary pipe in order to get a water from a reservoir through pump, and then transfer or supply it to the remaining water supply system. So what I did, I calculated the elevation of pump reservoir using a T-Rex tool. I made a selection of these two elements, and then using that selection, I just calculated the elevation of these elements, and then using these elevation, I calculated the water level, the pump level. So basically, this is the ground elevation where I have to construct a tube well. This is elevation basically I have calculated using a T-Rex tool in a WaterGEM, and then the water level is calculated. I am assuming here that the water level is below 200 feet, the ground level. So based on that, I calculated the water level, and then I calculated the pump level, that where the pump should be kept in a tube well below the ground level, because the pump is submersible. So 200 below is the water level. I am assuming the 50 feet of drawdown. When the pump's working, there will be drawdown, decreasing the water level in our tube well. And similarly, I assuming a 20 foot of factor of safety to keep or to place a pump in the water below the ground level. And then I calculated the difference between the highest junction level in the system and the tube well where I have construct the ground levels. The ground level where I have to construct a tube well, and then the highest junction will junction elevation. I just find a difference in between these two to calculate this value, and based on this value I have to calculate that how much head of pump we should select in order to fulfill the demand. So when we supply a water to water supply network, there is a minor losses, head losses. So I also considering these head loss parameters. So I just assuming the total head of 354 and then add the head losses with this. So basically uh, to calculate the head required for a pump, that how much head of pump will be required. So basically 200 feet is below the water level, and then 50 feet of a drawdown and 20 feet of a factor of safety, and then adding the difference between the ground level of tube well and the highest junction level. So we get a head, and then I just assuming that there is a 300 feet of head loss will be occurring when the water flew through pipes. So we get the total dynamic head of 654 feet. So based on this value, I will select a pump. And similarly, when I connect a pump and run a model, I may get a total, this is basically gallon per minute, a maximum value of 908 gallon per minute, or I can also use this maximum value, maximum value in order to get. So I'm taking this value, for example, 2500 gallon per liter per minute. So in different unit it gives. So basically here is in gallon per minute. So I have to find that how much should be the capacity of a pump that it should pump it to the network in order to fulfill the demand. So I have to calculate that. So if I convert these values and add some factor of safety in that as well, I have to also consider a factor of 1.5, because in the diurnal patterns here this value is basically calculated on basis on the maximum day value. And then in a diurnal pattern you can observe that when these value, for example 1.45 is multiplied with this value, or these values, these are all the same values, then it will increases. So based on that volume of water or the demand of a system, we have to select a pump. So I just took a value of about 3000 liter per minute for a factor of a safety, and then convert it into the gallon per minute. You can easily convert that in using different conversion tools. For example, here I am just taking for example, this is capacity here. The capacity of a system is about 840 gallon per minute. You should keep also some factor of safety in that as well. So by projecting it to vertically and then projecting on the y axis, we should take such pump in order to fulfill the demand. So we know that the head required for a system we calculate is about 6454 feet. So based on that, I took the pump of about 660 feet of our design value. So basically, this is the curve. This is basically the curve which we will use. For example, this is a curve which we will be using for in a WaterGEM. So I use these value. I want to show you that as well. So by going to the pump definition, I defined the pump curve by using 3 points. So shut off head is about 80 feet by taking the values from here. That for this pump, the 880 feet have a shut off head having zero supply of water to the system, and then use a design value of about 660 feet, giving capacity volume of water of a discharge of water to the system. of about 840 gallon per minute. But one point should be kept in mind, that I am just very exaggerating these values, because you should also to consider that how much you should the water will be yield from from the tube well. For example, if the total capacity of a well is about 600 gallon per minute, and you are using a pump of such value that is greater than that, then the drawdown will be very high, and the source will be scarce after 2 or 3 years. Therefore, you should consider that point as well, the yielding of water from a, or the discharge of a water from a reservoir. And then I just put a value of the maximum operating point, having a capacity of about 475 gallon per minute, having giving a head of about 340 feet. So these are the values where which I enter here, and also the efficiency have been calculated uh, by using by projecting downward. These are the curves for the efficiency curve for the pump. So I took the value of about 80% of efficiency for the value of 840 gallon per minute. I just put in here. I didn't use the NPC net positive suction head. You can also use this. I will provide you the this file. Basically, in a previous lecture, I used the the pump catalog provided to me by the Mr. Taula, but that was not appropriate for this system. Therefore, I found in from the internet somewhere. Basically, this is the Canadian company in Canada, but I want to show you that these type of curves may be available for you in order to design the water supply system in Pakistan as well. Okay, so I have defined the pump for the water supply network, and then I want to show you something, that the demand. Basically, I want to show you just that how should the pump should be designed. You will have to optimize the whole system by yourself, because it will take more time. It may take up days or 2 days. So it's upon you that how you work on it. So these are basically the different values. I want to annotate. So this basically color coding of different values or nodes. So want to convert it 20, 50, 80, and that's it. So we should design a water supply network that the pressure on each junction should be in between the between 20 psi and 80 psi, not less than 20 psi or not greater than 80 psi. If the pressure increases greater than the 80 psi, what will happen, that the bursting of pipes will occurs, and if the pressure is less than 20 psi, then it will cause low head, providing low head for the customers connected to that junction. So this one should be remembered now to design the water supply network. So I am taking a black value for here, apply. نو سنټ کیږي ولې نه یار؟ جنریټ کیږي ولې نه؟ ټول ټایم خراب دی یار. پرون هم دا مسله کوله، اوس بیا دا مسله کوي. کله چې دا ولې وختي ټیک کړې مې وه.
annotation
دا کلر کوډینګ نه کوي کنه، مونږ ته پته ولګي چې څونه کم ځای کې.
خبره خو سمپل ده
نه راځي نه کوي نه کنه،
اپلای کیږي
اپلای کیږي نه.
دا سټیپس نه کوي.
نه نه دا څه مسله نه ده خو دې کې. صبات خان صاحب داسې کومه زه چې ماته مسلې راشي نو بس ګرځو پسې بیا.
documents friendly طریقه خو یې په دې دیم دا خی اوس اپلای کیږي نه.
دا کمیونټیز دي کنه جی.
حاجی کمیونټیز
دا څه وجه ده؟
बंद कई सर गए वो ओपन कई
دا پرشر ډیر زیات په دې راځي کنه، نو زه چې دا خول غواړم اوس بیا خوند نه کوي.
माजी फाइल बंद कई ओपन कई दिस
نه نه هغې مسله نه ده جی دا. أسطول time خرابي سوق كمان. لا هو طول time على خراب.
Da بتاسو به اډ کوی.
اوس اپلای کړه. ها زه پوه شوم دا. او چې کم رینجز ورکول هغه نه دا ډېر زیات سیوا دي کنه. ها
رینجز څنګه څه ودی سر تاسو خپل ډیزایر رینجز دا دي کنه
دا به سیټ کوو کنه جی
2080 خو تاسو ور کړو نو ښه 380 تاسو نو ور کړو
او میکسیمم ویلیو مې ورکړه 380 پورې پریسر رسي دا وایبل نه دی هغه ټول دی رینج کیو نو بلیک کیو نو بس ټول بلیک کاري دا so now I just want to show you that by color coding and by using extended period simulation you can observe that the pressures at each junctions. So the pressures are very high. Basically, I think I have select such a pump that have providing a head of very high value and other point as well that I didn't design pipes for the system. I want to show you that as well. So by selecting a pump table, you can observe this most all of the pipes are of 100 millimeter. So by decreasing the die of pipe, the pressures at each junctions can be decreases. So I will provide you the model and do that by yourself because it will take too much time in order to optimize the whole system. And I want also show you to how to design an intermittent system. So this is basically the continuous and 24-hour supply system in order to supply your water throughout the day through a pump. So now I want to show you that in an intermittent system, basically, when you want to design an intermittent system, you pump water for some hours and then turn off the pump. Basically, in Pakistan, such intermittent system are basically more used. So here I will show you that how to, for example, how to design a pump in an intermittent system. Then you have to provide a controls for that pump. So I'm going to provide pump controls to this pump. And one thing to remember that if you want to design a water supply network, then it is not appropriate basically to use such pump that draws water at a very high rate. Therefore, if not feasible, that much and not for example, in most of the cases that the pump will be not available. Such type of pump that draws the water at such a high volume and providing for such high head. So you can observe here that it is basically the 10H die of pump. So the 10-inch dia of impeller basically. So this are very will be very expensive and as well as mostly maybe not find easily in Pakistan. Therefore, you have to select number of pipes and number of tube wells in a network in order to fulfill the demand. So now I want to show you that, for example, I want to show you that mostly, let me show in Excel. You can observe that the demand from 12 a.m. to 4 p.m. is very low, and then it increases up to 9 p.m., 9 a.m., and then the value again decreases up to 12 a.m. 12 p.m. and then again increases up to 15 p.m. So we have to design an intermittent system in such a way that the pump should on in between these time and in between these time and in between these time. So how to make this in a WaterGEM? So I have to provide controls in such system. So I will create a controls, logical controls, new simple condition. So what you will have to do, you will just click on the controls, find in the home tab, and then you will create a logical logical control, and then you will provide a control to that pump that for example that the pump should be open from this time to this time and should be closed from this time to this time. So at the start of simulation I want to close it by the status. Okay, basically, so when the simulation started, I want to make it off and want to give a control that at the time of 4 a.m. for example, if I want to first you have to first select the pump element. After selecting a pump, what you will do, clock time. You will create a new simple condition from here, then select a clock time, and when the times equals to 4 a.m. okay, then what you will do, you will create a condition, then here you will select a pump. So when the times equals to 4 a.m. the pump should on. This is the one condition. At the 4 a.m. the pump should on. I want to add another condition. I will create a condition, clock time. If for example, if you observe here that at the about 9 a.m. or 8 at 8 a.m. the demand decreases, so therefore I will give it a value of 8 a.m. the pump should off. Now again I will create another condition for a pump, new simple condition, clock time equals to from here you can observe that at about 11 a.m. the demands again start to increase. So at the 11 a.m. I want to open 11 a.m. I want to open a pump. So the when the time reaches to 11 a.m. The pump will start, and I want to give another condition that if the time reaches up to 2 p.m. or 12 14 hours, 2 p.m. the pump should off. No, yeah. Okay. add another condition, clock time equals to equals to 2 p.m. When the time is equals to 2 p.m., the pump should off, and from here, when the